Hi, and welcome everyone to this week's One World Mind seminar. It's my great pleasure to introduce our speaker, Dr. Jeff Calder, who's an associate professor of mathematics at the University of Minnesota Twin Cities, where he has been awarded an Albert and Dorothy Martin professorship. His research involves interactions between partial differential equations, numerical analysis, applied probability, and computer science. Dr. Calder's research has been funded various times by the NSF, and he has been awarded various fellowships, such as from the Alfred P. Sloan Foundation and the McKnight Foundation. He's also the creator of the Graph Learning Python package, a significant software contribution to the graph-based learning community. So today we're pleased to hear him talk about PDE theory and applications in graph-based learning. I'll turn it over to you now, Jeff.
Okay, yeah, thanks for the introduction, and for being invited to speak. I think it's been a few years I've spoken at One World's seminar, maybe 3 or 4 years ago. I think when it started, maybe in 2020, I guess. Um, so I'm going to just talk about some of the things we've done recently, like in the last few years. Feel free to jump in and ask questions anytime. I'm not too sure if I can easily see them, but I'll try to keep an eye out. So just to sort of jump back to a really high level, we can talk about fully supervised learning, which is if I have a collection of data, I have data like xi and I have labels yi, and the goal is to learn a function f that maps the data to the labels. Okay, so that f of xi is equal to yi, with the hope that it will, give me the correct label for new data that's not been seen before. And so this is often done by minimizing a loss function. So you choose some class of functions f parameterized by some weights theta. You choose your favorite loss function and you average over the training set, and you get a loss. And you minimize this over theta, and then you see if this model works well on real data. Oftentimes, nowadays, this f would be a deep neural network, and there would be millions of or even more weights in this parameter theta. So, for instance, if you a sort of very classical problem now is the ImageNet problem, where you're trying to classify images, and so the input is xi would contain all the pixels in an image, and the output would encode, say, the label of the image. Like here, it's which breed of dog is in the image, and these are all ImageNet images, and there's something like 14 million images in ImageNet, and there's 20,000 different classes, and so it's not enough to say it's a dog. You have to say what breed of dog it is as well. So if you have, large amounts of labeled data, you can use deep learning approaches like this, and they work really well. But you need really large amounts of data for this. And in practice, it's much more common to have limited amounts of training data. Limited amounts meaning like maybe 100 or 1,000 labeled examples, where you can't train a deep neural network without having problems like overfitting and so on. And so there are many different approaches you can take with limited labeled data. The one we'll talk about in this talk is called semi-supervised learning. And here the idea is when you have small amounts of labeled data, you might also have very large amounts of unlabeled data. That would be like a lot of images, of the similar type to what you're trying to classify, but without the labels attached to them. Okay. And so the idea in semi-supervised learning is to use some additional, possibly large amount of unlabeled data to improve the learning outcomes you would get, versus just doing fully supervised learning where you only use the labeled data. And the way that you do this is called the semi-supervised smoothness assumption, which is that you impose that the label predictions you make, they should vary smoothly in dense regions of the unlabeled data. Okay, so you don't want the label decision to sort of change abruptly in some dense region. A picture you could sort of keep in mind is if I have a toy example here where I have two labeled data points, that's the blue circle and the green square. If I ignore the black points for a sec, those are the unlabeled data points. Then if I only have these 2 points and I try to classify, new data points in the plane, the best thing I can kind of do is to draw a line between them, and say anything on one side is green, the other side is blue. Okay. But this line would sort of cut through a dense region of the unlabeled data, and so it might not be the best thing to do if you had access to the unlabeled data points, these black points. And so these are the only points, the black points in this figure are the unlabeled points, and these are the only ones that you're going to want to predict on after you train your model. And so what you would want to do in semi-supervised learning is to train a classifier that respects the nature of the unlabeled data in the sense that it cuts, in sparse regions. It doesn't cut through dense regions of the data, and so it satisfies the semi-supervised smoothness assumption in this setting. We'll keep this in mind at a high level, and we'll see sort of how do we do this in practice. Okay. Of course, there are lots of applications of semi-supervised learning. A very small list here includes classification of web pages, academic papers and images, and many, many more applications. Okay, so one way that you can use unlabeled data in a semi-supervised learning problem is to build a graph over that data set. So here's an example of two different toy problems. This is the 2 moons data and the 2 circles data sets. And here I have like a k is equal to 6 neighbor graph, I think, over this. So you take each point and connect it with an edge to its like 6 or 7 nearest neighbors. And now the idea is once you build a graph like this, then you can sort of translate this idea of semi-supervised smoothness. You can translate it into a stipulation about how the labels should vary smoothly over the graph in some sense. And then you can sort of, it becomes easier to mathematically say what that means. Yeah. Now, in sort of practice, let me give you a concrete example of how you might build a graph. So this is a very sort of toy problem called MNIST, which is it's a collection of 70,000 images of handwritten digits. These are all 0 to 9. You can see sort of a collection of 100 of them here. And the task is to take the image and to classify, to say which digit belongs to that image. So the label is the actual digit 0 through 9, and the input X is all the pixel values for that image. Okay. So really, this is like a fairly high-dimensional problem with the, vector X lying in R784. That's 28 squared. A sort of very naive way you might build a graph is an epsilon ball graph where you choose a bandwidth epsilon and you choose the weight between two images to be some kernel, oftentimes like e to the minus t, applied to the distance squared between the points divided by the length scale. So you only connect points that are within epsilon to each other. In practice, because these images or this point cloud can be very sparse in places and very dense in other places, it's usually more practically meaningful to build a k-nearest neighbor graph where you adapt this length scale epsilon locally to the point cloud. And so one thing you could do is to choose this epsilon to be like the distance to the kth nearest neighbor for x or for y, and if you just multiply them, it becomes symmetric. We'll talk later in the talk about sort of more practical ways. This works really well to build a graph over MNIST, but MNIST is sort of highly pre-processed. The images are all the same size and they all have the same, brightness. The digit's always in the same place and the same size in the images and so on. So this works very nicely on MNIST. We'll see later that you have to do a bit more work to build a good quality graph over like a real image problem where the images are more complex and maybe have more natural image features and so on. Okay, so the idea in graph-based semi-supervised learning is you're given a symmetric weighted graph. So the nodes are X and the weights are W. You have labeled nodes. So there's a subset gamma of the graph. And on this, possibly very small subset gamma, you have labels. The labels are given by a function g from gamma into rk. We usually take vector valued labels, which means like the one hot vectors like e1 through ek denote the k different classes. And the task is then to extend the labels from gamma to the rest of the graph. Yep. And of course, the goal in this semi-supervised context is to use both the labeled data, that's the small subset gamma, and the labels g. So to use the labeled data and to use the unlabeled data, so the rest of the graph. So the whatever structures appear in this graph that you're given. And so the idea here, if I take the previous example from a couple of slides ago, I build a graph over this two moons problem. I have two labeled nodes, the green square and the blue circle. And then I build my graph, so you see all the edges here. And then what you'd want to do is to propagate these labels. So the green one propagates along the lower moon and the blue one propagates along the upper. I chose, labeled nodes that are fairly hard for this problem because the green one's as far as you can get on one side of the moon, and the blue one's, as close as you could get on the other one. So it's fairly hard to classify correctly with these two nodes compared to if you choose things like in the center of the two moons. Of course, we'll get to this later in the end of the talk. If you had the possibility to sort of choose which nodes to label in each cluster or in each class versus just having them assigned at random or something. This is the context of active learning that we will talk about. And here you can do a lot better, actually. Okay, so one of the oldest and seminal methods for graph-based semi-supervised learning is called Laplacian regularization. This dates back to 2003. And the idea is to take the harmonic extension of the labeled data, G. So you solve the equation Laplacian of U is equal to 0 on the unlabeled data, and you fix, U is equal to G on the labeled data points. Okay, so you're finding in some sense the smoothest function because we think that harmonic functions are nice and smooth, but we'll see this might not be exactly true in a second. This L is the usual graph Laplacian. Keep in mind that this function U, it's a label function, so it's mapping into RK. And so this is all vector valued sense. Because it's vector valued, you have to predict a label for each node at the end, and you just simply do this by thresholding. So you take the argmax along all of the components of the output U of x. Okay, so of course there's always some variational interpretation for Laplace equation like this, and here it's exactly equivalent to solve this optimization problem in place of doing the harmonic extension. And here the variational problem is to minimize this energy over the graph, which is the sum over all the edges of the difference in the label vector squared times the edge weight. So you minimize this energy, which sort of measures, how smooth the function U is over the graph, subject to the function U agreeing with the labels at the labeled nodes. Okay, so again, it's the idea of choosing the smoothest function with respect to the graph structure that agrees with the labels. And of course, there are many, many variations of this. I just wrote down one version. This is like the first version that came about, but there you can write down, 10 different variations of this where you change, how you normalize the graph Laplacian or how you encode the labels. You can put soft penalties on the labels and things like this. Okay, so it's important to point out there's also a random walk interpretation. So you can say there's this Laplace equation, there's this variational problem. There's also a random walk interpretation of this equation. So if you take U to be the solution here, Laplace U is 0 on the unlabeled nodes and U is G on the labeled nodes, and take a random walk on the graph. This is the usual random walk where the probability of going from X to Y is proportional to the edge weight.
You don't feel annoyed?
What is that? No.
This is a seminar. It's talking about
Oh, is there a question? Sorry. Okay. Okay. I'll just keep going on. So we take a random walk on the graph. This is the usual random walk where the probability of going from X to Y is proportional to the edge weight. This turns out to then be a martingale. So the expectation conditioned on xk, the expectation of U at the next step remains unchanged, essentially. So you have nice averaging properties along this process. And you can get this directly from the property of Laplacian U is equal to 0. Okay. And so what you can say is that, okay, if you choose any stopping time, okay, here I'm going to choose the first time that the random walk hits the labeled nodes. Then the expectation of U at the stopping time is the same as U at the initial time. So U of X is the expectation at the stopping time, which is just the expectation of the label vector that you hit. Okay. So you can think of Laplace learning as just you take a random walk. If you want to label the node X, you take a random walker, release it from X. You see which labeled node you hit first. Okay. That's this G of X tau. And you do this over many, many realizations of random walks, and you average all of them. And so in some sense, you're kind of like using random walks to explore the graph structure locally nearby, like which nodes and which clusters can you get to easily with random walks, and you average that according to, what's the probability of the random walk hitting each of these labeled nodes. Okay. So it's a very sort of, reasonable thing to do in the graph setting. Okay, so this, it works. This method works really well if you have, at least, low to moderate amounts of labeled data. So if you look on this is on MNIST. If you look at the right side of this chart, so that's 1,600 labels, which is 160 per class. You get 97%, which is about the most that you can do without using some additional features of the data that you might extract using neural networks, let's say. And this compares to, say, like a graph nearest neighbor classifier that gives around 92. So these are good results at those label rates. But if you go to very, very low label rates, so here I'm going down to one label per class. So I just give you one example of a 2 and one example of a 6 and one example of a 7, so on. The accuracy is very poor, so 16% compared to a graph nearest neighbor classifier that again should be some kind of baseline for us, just choosing the nearest point in the graph distance. Okay? Which is like 65%. Okay, so something is going like terribly wrong at these really low. You should be able to do much better than this at 10 up to 40 labels per class. And so if you think about what's happening, okay, we were thinking that we were getting this nice smooth function that extends the labels, but this is actually not the case when you have very, very few labeled nodes. So it turns out that if you have too few labels compared to the unlabeled nodes, then instead of the harmonic extension being a nice smooth function that interpolates, it becomes roughly constant, and then it will attach a spike at each labeled node, where the spike is oftentimes just like a single node in the graph. So at the single node, you agree with the correct, u is equal to g, and all the neighbors you can just plummet down to the average value essentially. And the reason you see this, okay, you can look at it in two different ways, right? You can look at it through the variational interpretation here, is that the constant function minimizes this energy. It's like the smoothest possible function over the graph is the constant one. And the only reason you can't use the constant is because you wouldn't agree with the correct label values at the labeled nodes. Okay. But okay, so you take the constant and then you just add a spike at the labeled nodes, so you agree with that. And if there are few enough labels, then the cost of these spikes is sort of small enough that it's cheaper to do that than to give a smooth interpolation. Whereas with a smooth interpolation, you'd have energy sort of spread over the whole graph and not just concentrated on these spikes. In terms of the random walk interpretation, okay, what you can think is that if there are too few labels in the graph, then what happens with this random walk is that it takes too long to hit a labeled node. Okay, so it basically explores the graph for too long, and you reach the mixing time for the random walk. And once you've done this, you sort of, the random walk has forgotten where it started. And so essentially you're just averaging over here against the invariant measure for the random walk on the graph. And so you get a constant essentially over the whole graph for that reason. Okay. But of course, if you add more labeled nodes, these problems all, get better to the point where, you might be happy with the picture on the right side where there's 1,000 labels. You might be somewhat happy in the middle because you can kind of see the underlying label function, and you might be very upset with the one on the left-hand side. Okay. Okay, so to say a little bit about, how this, like why this is happening, we switched to sort of take the perspective of like the large data limit of these problems. And so we're going to study this on a type of random graph called a random geometric graph. So here we take the nodes in the graph, the vertices, to be a sequence of IID random variables on some subset of omega. We could also take a manifold sitting in RD, and things are not so much different. And they'll be drawn according to this function rho, okay, which is the probability function for the data. We will take to build the graph, we'll use the epsilon ball graph we talked about before, where I choose a kernel eta and a bandwidth epsilon, and I connect 2 points with an edge if their distance is less than epsilon, let's say, with this edge weight here. And then in this sort of nice setting, which sort of agrees with how we build graphs oftentimes in practice, the question is if I look at these graph-based learning problems with a very large number of nodes, so say like a very large number of unlabeled nodes compared to the labeled ones, which is the setting we are looking at before. What happens if I just take the limit as the number of nodes goes to infinity? And the graph bandwidth, tends to zero, so things localize, basically, so I keep a sparse graph structure. Then I expect to get some continuum problem on the domain omega, maybe like this eigen value problem I wrote here, but this is not the exact thing that we'll see momentarily. And the idea is, here you can use some analysis from the limiting problem that is more difficult to apply in the graph setting. Okay, and you can then draw some insights that can sort of be pulled back to the graph problem. And actually, what's really interesting for me is to use these insights from the continuum limit to design new algorithms on graphs that perform better sort of in these large data limits. Okay, so on these random geometric graphs, we can write down the graph Laplacian. It's the same Laplacian we had before, but we're putting the weights, this eta of x minus y over epsilon. We stick this in and we add some normalization factors to make it converge to a limiting operator. And let me just go through this kind of quickly here. So if you want to see what is the limiting operator for this graph Laplacian, well, there are sort of two steps you have to take. One is that, this is a sum of IID random variables. You can take the expectation of this, and this is sort of the first step. So if you take the expectation, the 1 over n goes away, and the summation gets replaced by the integral against rho over here, dx. And then you can control the errors here, if you like, with things like concentration of measure results. And I'll go into that maybe a little bit later on in the talk. And then after you've done this step, now you have this sort of non-local operator here. You can now do a second order expansion for u, like assuming it's smooth. So here I said C4. C4 is to get, this epsilon squared error rate. You could also take C3 or C2 alpha would be enough in this case. So you do a second order expansion for u, and actually rho has to get a first order expansion here. And you sort of multiply everything out, and when the dust all settles, what you get is this operator rho inverse div rho squared grad u. Okay, so it's a second order elliptic operator, but it's not the usual Laplacian. If you had uniform data where rho is equal to 1, you would have the usual Laplacian, but here it's weighted by the data density. Okay? And so the idea is that in the limit, what you're expecting that you get from Laplace learning is this weighted elliptic equation, but it's still like a harmonic extension of the data, where you impose the labels on this subset gamma, which we haven't quite specified how that appears in this limit. And of course, this also has a variational interpretation in terms of minimizing an energy that involves grad u squared, but you're multiplying by rho squared here as well. So that's one of the first insights you can sort of draw from this, is that in the limit, you're seeing the data through this through rho, actually rho squared, appearing in the limiting variational problem. Which means that if I'm minimizing this, okay, I'm trying to sort of cut the data, so I need u to be like piecewise constant in some sense. So it's like 1 on one cluster and 0 on the other. And I'm trying to figure out where I should cut, right? Where I should make the gradient large. And okay, the place you should make the gradient large is where rho squared is small. So I have a small energy here. And rho squared is small precisely when I'm sort of in the sparse areas between clusters. And so this tells you that the method has the capability of sort of cutting between clusters and not, through high density regions. The issue though becomes that this data u is equal to g on gamma. The set gamma needs to be sort of relatively large in some sense for these problems to be well posed. And if it's too small, like if it contains isolated points, then the limiting problem is ill posed, and actually it forgets about the labeled data. So if gamma is too small, you can kind of erase that line. In the limit, you just get the elliptic operators equal to 0, so you get a constant function. And this, in some sense explains the spikes. In the limit, the spikes are kind of vanishing, and I'm converging to a constant, which is the solution of the equation without the labeled data condition. Okay, so this is a problem that we've been working on, for some time. It was proposed, it was pointed out. I forget if there's a footnote here somewhere. There's a paper by, yeah, here. There's a paper like in the bottom of this slide by Boaz Nadler in 2009, where they first pointed out this problem with the spikes and with the limit of small labeled data to infinite unlabeled data, being sort of a problem in semi-supervised learning using graph Laplacian. So that's around 2009. And it's been, about 15 years or so of various people, including myself and others, have been working on this problem. I won't really go in chronological order. I'll just say, I'll go in sort of more logical order, let's say. Um, One thing we did sort of more recently was to analyze, the size of these spikes in a sense. So to ask the question of, um, how many labels do I need to ensure that I don't have these spikes forming, and so I can give a well-posed in a sort of well-posed smooth extension of the labels using Laplace learning. And so what you can prove is this, you can sort of, figure this out through a rough argument balancing, what would the variational energy be for a spiky function versus a smooth function that sort of um, it extends the data well. And you can sort of balance these two terms and say, okay, I'm going to sort of grow these spikes until the energy of the spike solution with the smooth solution sort of balances. And what you find is that the height of the spikes should be proportional to the bandwidth of the graph divided by the square root of the label rate. Okay. And then you can actually, in this paper I mentioned here in 2023, you can actually prove this rigorously. And for that, we actually used the martingale techniques and the random walk interpretation of the problem. And so what this says is that if you take a large enough label rate, and this is not like all that large in some sense, this is that, label rate should be much bigger than the bandwidth squared, then you get a well-posed limit. These spikes vanish in the limit and everything's okay. And so this means that even as you take this limit as n goes to infinity, epsilon goes to 0, you can even allow your label rate to vanish in this limit, but it can't vanish too quickly, essentially. Sorry.
Excuse me, Jeff. We actually have a question in the chat.
Okay, sure, go ahead. I don't see the chat for some reason. Yeah.
Sure. The question is, are you talking about the Laplace operator in 2D, or could it be d-dimensional space as well?
Yes, it's in RD. Yeah. All of my figures, sorry, I just actually, all of my figures are in R2 just so you can visualize things. But the problem is posed like this set omega that we're working on is just in RD. Okay. And D could be quite large, possibly. Yeah. This thing with the spikes that you're seeing occurs, for any value of D, but it's easier to sort of draw these figures in R2. It actually is worse when D is larger in some sense. So when you're in R2, it's kind of borderline in the sense that, the number of, this is not maybe so clear from this result here. Let's see. But in R2, it's like if you have n points, then you need only sort of log n labeled data points to make it well posed. So it's very, very borderline in R2. When you make D larger, this gets worse, essentially. Does that answer your question, or?
Yes, thank you very much.
Yeah. Okay, so since the initial paper by Nadler, one of the first attempts to address this was Zhu in 2011, where they said, let's solve the higher order version of the Laplace equation instead. So let's solve Laplacian to the m of u is equal to 0. And why would you do this? Well, there's this thing called a Sobolev embedding. If you take a higher order Laplace equation, you expect to be in the higher order Sobolev space. So u should be more regular in a sense. And if this m is large enough, then you have a Sobolev embedding of this Wm2 into a Holder space C0 alpha, where this is the space where you have Holder continuity of functions, and that means that you can't have spikes forming. So you have some lower bound which looks like a cusp, let's say, for your function behavior, but it can't be a very sharp spike. Okay? And here you have to have m is bigger than 2d to make this work in theory, for arbitrarily small amounts of labeled data. And there's some very rigorous, there's some nice rigorous analysis of this very recently in 2023 as well. It's actually a pretty hard problem to analyze rigorously to sort of show that you have a well-posed limiting equation when you take finite labeled data and infinite unlabeled data and take this M to be sufficiently large. There's the p-Laplacian was proposed shortly after that, 2016. And we've worked on that quite a bit as well. Here you solve the p-Laplace equation on the graph, which is a nonlinear equation now. So the higher order Laplace equation is just to take the mth power of a linear operator, so it's linear as well. The p-Laplacian is highly nonlinear now. But again, for the same kind of reason. So here, if you make p large enough, here it's p is bigger than d is like the threshold, then you have a Sobolev embedding of into Holder spaces again. And so you expect that you have some Holder continuity and you can't get spikes forming in these solutions. Now, okay, so we did work on the p-Laplacian, and we've sort of tested a lot of these algorithms, and I'll show you this later on as well. Both of these, I would say, higher order regularization and p-Laplacian are a lot slower to solve numerically, because the higher order one is still linear, but it becomes more poorly conditioned as m gets larger, and the p-Laplacian is nonlinear, which makes it harder to solve as well. And so, after doing a bit of work on these problems, we were just sort of playing around with the original Laplace learning and trying to kind of tease out why it's so ill-posed at these low label rates. And we did something really, really simple. What we did was we said, after I solve the Laplace equation, before I threshold, like before I take the argmax to make label predictions, I'm going to center the solution. So I'm going to subtract the mean vector over the graph. So it has mean 0 now. And the accuracy was substantially improved, to say the least, like from 17% up to 91%, essentially. And up to the point where 50 labels were getting almost 97%, which was the accuracy with 1,600 labels before. Okay. So, what this was saying to us was that, okay, these spikes that are showing up, the picture is maybe not necessarily as bad as what you see on the left-hand side here, but these spikes, even though they're causing some kind of issue with the method, the tail behavior on the spikes is sort of, contains enough information to classify properly, but in some sense, there's some huge offset in the solution. And this huge offset is what is causing the poor accuracy and kind of, pushing all of the labels into one class in some sense. Like this is, if you made the same prediction for everything on MNIST, you would get 10% accuracy. And this is getting very close to that, being 17%. And so, we were working on this for quite a bit and trying to see, like, if there was some way to interpret this centering step. What we didn't really like about it was that, if you solve the Laplace equation and then center by the mean vector, what you're really doing is solving the Laplace equation with shifted labeled data. So it's like you're shifting the labels by this vector c, which is just essentially chosen so that the mean of the solution is equal to 0. And okay, so you can do that and you get better results. But it seemed to me to us to be not well motivated in the sense that like you're now doing the harmonic extension, but of the wrong labeled data. So you're sort of modifying your data, making it incorrect in some sense, and then doing the extension of it and getting better results. So we played around with this for a little bit. And it turns out that there's another equation lurking underneath this setup. So what you can say is, if you do really have this really low label rate setting, where you have spikes and this constant u, which if we do the centering, that constant is around 0. And then you have these sharp spikes to attain these shifted labeled data points. Then actually it turns out that you can approximately compute Laplacian of u on the labeled data as well. So the argument is here. It's very short. You just write down Laplacian of u, summing over the neighbors in the graph. And the point is, if you're at a labeled node, you're at the top of that spike or the bottom of the spike. All your neighbors are going to be at the constant value or close to that constant value u is equal to 0. So the neighbors are the u of y. So all the u of y's are 0 in this sum. And all the u of x's are the shifted g minus c. So that's the g of x minus c. And then you can sum over y, and you just get the sum of the weights, wxy. So that's d of x over here. And this is something which doesn't depend on u anymore. Okay, so we have a right-hand side for the equation. So it turns out actually that in these very low label rate problems, Laplace learning approximately solves this Poisson equation, which is an equation with Laplacian u on one side and a source term on the other side. And here it's the source term on the right-hand side that encodes the labels in the problem. We modified this a little bit because we found it gave better results. We got rid of this d of y, which kind of just, puts more weight on labels that have more neighbors, which we didn't think was always important. So we dropped the d of y. And the idea is now, okay, so here's the equation on the next page, is that instead of doing Laplace learning, we do Poisson learning, which replaces the hard labels where you're fixing u is equal to g at the labeled nodes. It replaces that by point sources and sinks on the right-hand side of this equation. So you solve the equation over the entire graph, and the locations and the values of the point sources and sinks encode the labeled data. And now the mean zero condition from the previous slide and the centering conditions are all sort of exactly the necessary conditions for existence uniqueness of an equation like this. So they're sort of very naturally arising in this setting. And of course, after you get this equation, you can go back and say, is there a variational interpretation of this? And there is. So the first term is the same. You're still trying to minimize this smoothness functional over the graph. But the second term, which comes from the source term on the right-hand side, is a linear function of the labeled data, and it's just the dot product between the labels and the shifted label vectors. The minus sign here just means that you're minimizing, so it means you're maximizing the dot product, so you're maximizing the alignment of the predicted labels with the given labels. And what's kind of neat here is that there are, there are other versions of Laplacian regularized learning where you add some kind of soft fidelity like this. Usually it's like the L2 or the L1 norm of u minus g. What's happening here though is that we don't have to include any kind of weighting term on this. So usually you put some weight like lambda on this loss on this part of the loss function. You could change that weight to trade off how much do I care about smoothness versus how much do I care about fitting labeled data. And in this case, actually, because this is a linear function of u, which is not very common in these loss functions, if you put a weight in front of the second term, all that you end up doing is scaling the solution u by a similar thing, by like 1 plus lambda or something. And so, you can change the solution u, but you don't change the label predictions. You don't change, that in the argmax, you don't change which class is largest, essentially. So there's no need to put an additional weight in here and no need to have additional hyperparameters. And in addition, because you're thinking of the labels as point sources and sinks, you can think about the total mass for these point sources and sinks in each class. And if you have unbalanced class sizes, so you have more labeled data in one class versus another, or the amount of labeled data in each class is not the same as the actual number of points in that class, then you can easily weight the point sources on the right-hand side so that the total mass in each class actually aligns up with the proportion of labeled data of actual data in that class. And if you scale the right-hand side of this equation into linear equation, it's the same as just scaling u. So you don't have to solve the equation again. You can just reweight u when you make your label prediction. And here it's reweighted by the ratio of the fraction of data in class J to the number of training examples in class J. Okay, so we talked about a random walk interpretation for Laplace learning. You can do the same thing here for Poisson learning, but it's sort of like the complete opposite point of view, I would say. So what you do is that instead of saying, you think back to Laplace learning, you take a random walk released from the point you want to label, and you see which unlabeled or which labeled point you hit first, and you average this over many random walks. What you're doing here is the opposite. You're taking random walkers that are being released from the labeled data points. So for each labeled data point, you take a random walker released from that labeled data point. So these labeled data point random walkers are exploring the graph, and they kind of carry along their centered label vector with them. And if you want to label a point X, what you do is you sit at that node X and you watch these random walks moving around. And whenever they hit your node X, you record the centered label vector and you add this up over, say, capital T steps of this process. And if you take the expectation of this and send capital T to infinity, you get exactly the solution to the Poisson learning problem. Okay? So it's like instead of releasing a random walker from the unlabeled node and seeing which labeled node it hits first, you're releasing them from the labeled nodes and you're seeing how they explore the unlabeled data. And what's really happening here is that the invariant measure for the random walk is being sort of canceled out in this sum. And so you're not seeing that sort of long-term behavior of the random walk, which is just this invariant measure that doesn't care where the random walk started. And you're really just seeing like the short-term behavior in this problem. Okay, so this can kind of explain a little bit about why this method can work well at low label rates. I'll show you some results in a little bit. But let me also tell you sort of the rigorous results that we can prove about the method. So what we can prove, what you'd want to prove is that if you take this sort of large data limit I was talking about before, and so you fix a finite number of labeled data points and take the unlabeled data points to infinity, what you would like is that your graph-based learning problem converges to a well-posed limiting PDE. Okay? And that's exactly what we can prove in this setting. So it doesn't matter how few labeled data points I have. If I had just a finite collection, so they're isolated points, I don't get these spikes forming like in Laplace learning where I converge to a constant. Instead, I converge to a solution U of a well-posed PDE. And actually, very recently, we have a paper proving a convergence rate between these two problems. So in the setting of finite labeled data and infinite unlabeled data, the graph-based learning problem converges to the continuum PDE to its solution in the L1 norm at a rate that depends on the bandwidth epsilon, but it's epsilon to the 1 over d plus 2 up to some log factors. And we think this is pretty pessimistic. We're sort of, current work is trying to make this rate independent of d, so something like epsilon or epsilon squared. But this is sort of our first effort in this direction. This holds with high probability over the choice of the graph, essentially. And let me say that the challenges here, I won't go into the proof in detail, given the audience in the talk, which I think is more broad. But the sort of challenging part in the proof is that the source term on the right-hand side is extremely singular in these problems. So in the limit, it's the Dirac delta measure, delta y, at the labeled data points over here. So the solution U to this limiting problem is not a smooth function. It doesn't even live in a Sobolev space, or not in a nice one like H2. It lives in one like W1P, where P is very, very close to 1. And so the best you can hope for is something like an L1 convergence rate. And that's what we have here. Actually, with this theory, we can get LP for P like a little bit bigger than 1, but it's a little harder to write down what this looks like. So the challenging thing here is, how do you regularize the equations so you get smooth terms on the right-hand sides, and you can apply sort of existing machinery to get these results. Okay, so let me say a little bit about some work we've done after this. So after we sort of figured out these Poisson equations for graph-based semi-supervised learning, we realized, there was a slightly older work that I had done in 2020, which we called the properly weighted Laplacian, which is another technique you can use to sort of overcome these spike issues at low label rates. And the idea in the properly weighted Laplacian was that instead of looking at a higher order Laplacian or looking at a p-Laplacian, instead you look at a reweighted Laplacian. So what you do is you take the usual Laplacian, but put some additional weights. Here it's gamma x plus gamma y for some function gamma, with the idea being that you're going to choose large values for these reweighting terms gamma. So you're gonna amplify the weights near the labeled data points, which is going to encourage the function u to be smoother, right? Because the weights penalize ux minus uy. Okay. So you make these weights heavier near the labeled points with the hope that gets rid of these spikes in some sense. There was a previous paper by Shi, Osher, and Zhu in 2017 where they proposed a simple version of this that worked well in practice in some cases, but was sort of still provably ill-posed in a sense. And what we realized here is that what you really have to do, right, is okay. So actually, this next equation says what I was sort of trying to say in words before, is that in the variational interpretation, the gradient, like ux minus uy squared, is being weighted by gamma x plus gamma y. So you're getting this extra weight from this function gamma. And if you choose these large enough, then you can penalize having a sharp spike forming. But it turns out that these have to be very, very strongly penalized. So this function gamma has to grow, has to actually blow up at the labeled data. And it has to blow up like the distance to the labeled data point in the ambient space to the power negative alpha, where alpha has to be bigger than d plus 2. So it's an extremely singular growth you need, and very, very non-local as well. And this is like essentially the scaling for the fundamental solution to Laplace's equation. So this is the usual blowup you would see for the fundamental solution. If you do have this fast enough blowup in this gamma, then you can show that the solutions to this properly weighted Laplace problem converge to this limiting equation, where it's div of rho squared gamma times grad u. So this extra gamma weighting shows up next to rho squared. And actually, this problem you can then prove, which we do in this paper. We prove that this equation is actually well posed, even if you have only like isolated finite labeled points in gamma. So you sort of resolve the issue with these spikes showing up. But the cost is that it seemed initially to us to be difficult to figure out how to choose this gamma function, because these are very sort of hard conditions to check in practice. I don't know, this data actually lives on some manifold. I don't know what the value of d is for the manifold. I don't know how to choose alpha in practice. I don't really know how to choose distance in practice sometimes too. And actually, this alpha might kind of have to change over the data set. It might be small or large in different regions and so on. And so sort of making one choice for it, or like treating it as some hyperparameter, doesn't necessarily work all that well. But we realized, after doing the Poisson learning work, that there's actually a really simple way to choose this gamma function. And we call this the Poisson reweighted Laplace learning, or PWLL. So it's the same reweighted Laplacian, but the gamma function is chosen just to be a superposition of fundamental solutions of the Laplacian on the graph. So you solve this Poisson equation on the graph. Laplacian gamma is equal to a source term on the right-hand side. We hear the source term doesn't encode the labels, but it encodes the locations of the labels. And in the limit, we would expect that this gamma would converge to a superposition of fundamental solutions to Laplace's equation, which have this correct scaling. They have this blow up at the labeled nodes that has the sort of exact correct scaling. Alpha is equal to d minus 2. So if you square it, so here we change from gamma x plus gamma y to gamma x times gamma y. So we get like the square of gamma. So here you get gamma squared in the limit. This should be strictly stronger singularity than you get in the fundamental solution. So it sort of satisfies the conditions in the properly weighted paper. So this new method, PWLL, it solves sort of two equations on the graph. You solve the initial equation to get gamma, and then you stick gamma into your Laplacian, and you solve this harmonic extension problem with this gamma. And in the limit, we would expect to get a coupled system of PDEs, but we don't quite have the tools to prove rigorously that both of these converge. So we can prove convergence of the first equation for gamma, but the L1 convergence is not really strong enough to stick this into the second equation. So this is sort of ongoing work to prove this, that the graph equation converges to the limiting one in this context. There are some relations to some things in PDEs recently, but let me maybe skip that and get to some results. Okay, and I'm going a bit slower than I had maybe planned to, so I think I'm basically out of time. Is that right, Kevin?
You got probably another 5 minutes.
5 minutes? Okay, okay, good. Let me talk about a few results. So, like I was saying before, it's only really on MNIST that you can build these really simple graphs, using the Euclidean distance between images. So we did some experiments with CFAR10 as well as MNIST and fashion MNIST. On CFAR10, these methods don't work very well. So instead, what we do is we learn sort of invariant features of the data in some sense. So using some deep learning techniques, we learn a feature map that takes images and maps them into a better feature space. And here we use some contrastive learning techniques. This one's called SimCLR over here. SimCLR basically tries to learn a mapping from images into Rn, which is invariant to a group of transformations, things like flipping images or cropping or doing some like shifting colors or doing Gaussian blurring, things like this. And if you look at, if you try to visualize CFAR10, these are t-SNE embeddings of MNIST and CFAR10. These are ways to visualize high-dimensional data. So you're sort of mapping into R2 while trying to preserve as much like local structure as you can. If you just work with the sort of raw pixel space for CFAR10, it's incredibly mixed up. So you don't really see any nice structure in the pixel space. Whereas if you work in the SimClear embedding, you see that it's almost, perfectly clustered. There's a few classes that are kind of mixed, but a lot of them are nicely separated. And so if you build your graph on the contrastive learning, like SimCLR embedding, you expect to get sort of much better results than if you build them on the raw pixel space. Of course, on MNIST, if you just, visualize the pixel space for MNIST, it's really, really nicely clustered. And so you can do whatever you want with MNIST and it works really nicely. So these are the results compared against a number of other graph-based learning techniques. We tested against more things in our paper, but there's lots of things that don't work well at all in this setting. And most of the time, one of our two methods works the best. The higher order Laplacian was very good on some of these problems too, at 40 and 50 labels. This is fashion MNIST. Actually, we used variational autoencoder embeddings for MNIST and fashion MNIST. For MNIST, it gives you slightly better results, and the fashion MNIST, somewhat better, let's say. And for CFAR10, it's the SimClear embedding. Okay, so let me say, okay, I skip all the stuff on the continuum limit here. Let me just say quickly that there's, we've been working recently on these problems in active learning where the problem is to sort of, not to assume that your labeled data is chosen at random, but to sort of have the ability to choose the labeled data points for a certain task. So the problem is that you start with a small amount of labeled data, you train a classifier, you make predictions on the graph, and then you want to say, if I were to add some of the unlabeled points to my training set, if I were to actually ask a human in the loop, what the label is for that unlabeled data point, which would be the best labeled points to include. And this is usually done in some kind of feedback loop where you add some points, you train your classifier, you get new predictions, you add some new points, and then so on. And you see, can I use these active learning approaches to get better results versus just, randomly sampling the points to label? And you can do much better in general. And what's nice about these methods that we've been working on is that they work well at very, very low label rates, at like one label per class and so on. So this is like the setting that you start the active learning process in. You start at very, very low label rates. And so you need methods that are well posed at low label rates. And let me just say that we've developed a method which we call uncertainty norm active learning that solves an equation very similar to the reweighted Laplace equation I just talked about, but we sort of add this diagonal perturbation, this tau times u term, which allows you to control the trade-off between exploring the graph and between exploiting the outputs of your graph-based learning classifier. And there are some nice theoretical results that you can prove about the ability of the method to explore versus exploit. And you can utilize the limiting PDE to prove these results. So let me stop, about there, but I'm happy to answer questions on. So there's some results on active learning in here from our paper, and I'm happy to answer any questions that you guys have.
Awesome.